This is the Unit 6 differential equation multiple choice review. So let's look at number 1. We have a of t equals 4t minus 1 and v of 1 equals 3. So this is kind of a particle motion PVA problem starting with acceleration and moving our way up to velocity. So we have to anti-differentiate acceleration to be able to move up to velocity. So we know velocity's definition is the antiderivative of acceleration. So from here I'm going to replace a of t with the specific expression. So now this is set up where I can apply power rule. 4t becomes 4t squared over 2, 1 becomes 1t, plus c will show up. And now clean this up, I get 2t squared minus t plus c. I have a general equation for velocity. I have an ordered pair. So 3 can go in for velocity, 1 can go in for t, and I'm going to solve for c. So 3 equals 2 minus 1, 3 equals 1 plus c. Subtract 1 from both sides, we get 2 equals c. So put 2 in for the c of our general velocity to get from our general equation to our specific equation, and that matches answer choice C. All right, number 2, we have dy dx equals y over 2 root x. And y equals 1 when x equals 4. Notice that we're given derivative and we're trying to get up to something in terms of just x and y. So we know we have to go through separation of variables, take the antiderivative, and solve this differential equation. So I'm going to cross multiply first so that I can get the fractions out of the way, hopefully make it easier for me to see whether I have full separation of variables, or if not, what else I can do to move things around. So cross multiply, I get 2 root x dy equals y dx. Now at this point, we see that we don't quite have full separation. Now dy and dx are in their correct locations, but things are still out of place. I'm going to go ahead and move that 2 root x over to the right side, and I'm also going to move the y to the left side. So we'll divide both sides by 2 root x. We'll also divide both sides by y. So I just did those two operations in one step. So that leaves me with dy over y is equal to dx over 2 root x. Now we have separation of variables, but these the location of these terms are not set up for antiderivative. Well, at least not all of it. This side is. Okay, so this we can think of it as 1 over y dy, which is natural log. But this, if I want to get it ready for power rule, I'm going to first push the 1/2 out in front. I'm going to bring the root x up as x to the negative 1/2. Now I can do natural log on the left side, power rule on the right side. So left side becomes natural log absolute value of y. The right side, I go through power rule, x to the 1/2 over 1/2. With the 1/2 out in front, plus c shows up. Flip that 1/2 to be 2. 2 times 1/2 is just 1. That goes away. Now I can exponentiate both sides, base e. And once I do that, I can clean up the left side. This cleans up to be just absolute value of y. The right side, e to the two exponent terms added together can be thought of as e to the x to the 1/2 times e to the c. And then e to the c is just a constant. I can multiply that, push that constant out in front. Now I have my general equation. I can also drop the absolute value. Now I can plug in our ordered pair. 4 plugs in for x, 1 plugs in for y. So 1 goes into the y variable, 4 goes in for the x variable. E to the square root of 4 is the same thing as e squared. And I can take that e squared, divide it over to the left side, make it e to the negative 2. So I can put this back in, put e to the negative 2 back in for my c. And so if e becomes e to the negative 2, now I have something that's in the form of e to the negative 2, e to the x to the 1/2, and that matches this form of e once I rearrange it, put that x to the 1/2 out in front. Remember, multiplying base is the same thing as adding or subtracting exponents, so we can go from here to here just using those exponent properties. Right, number 3. We have another differential equation. We have ordered pairs to help us out. So here I'm going to cross multiply, but first I'm going to rewrite it as e to the y over 1. Cross multiply, I get 1 dy equals e to the y dx. Notice that dy and dx are sitting in their right spots, but that e to the y is out of place. We want all the y's on the left, so I'm going to divide both sides by e to the y. We do have separation of variables, but this is still not in the appropriate location if we want to apply our antiderivative rule. So I'm going to bring that e to the top, make it e to the negative y. So now this is going to follow a u substitution rule. I can try to match this with e to the u. So once my u value is negative y, derivative is negative 1, make my substitution. I can get this into e to the u du with the dy getting replaced with negative du. I can push that negative out in front. And then integral of 1 dx becomes just x plus c. And now I'm going to go ahead and solve for c. So 1 plugs in for x, 0 plugs in for y. So e to the 0 is equal to negative 1 plus c. E to the 0 is just 1. 1 plus 1 is 2. And now I'm going to put this back in for the c where that belongs. And notice that this form doesn't quite get us to a y equals 2, but it's okay because we're just trying to match our answer choice, and the best fit that we see is going to be answer choice C. Okay. All right, let's look at next page here. Right, here's number 4. We have dy dx equals x over square root of 9 plus x squared. And y equals 5 when x equals 4, then x is equal to, then y is equal to. So again, I'm going to cross multiply. When I do, I get dy root 9 plus x squared is equal to x dx. I don't have full separation of variables, but we do have our foundation set. Now, the only thing that's left out of place is the square root. The square root has x's in it. We want that everything on with x's to be on the right side, so we divide that over to the right side. So now we can take our antiderivative integral of 1 dy, right? Put a 1 in front as a reminder that integral of 1 dy is just going to be y. And then here we can go through u substitution. We'll let the u value be the portion inside the radical. So we'll let this to be 9 plus x squared inside. Now this is really just going to be represented as, we can write that as 9 plus x squared to the 1/2. Let the u value be what's inside the parentheses. Find the derivative, du dx equals 2x. We solve for dx. We get dx equals du over 2x. We'll replace the parentheses with u. Replace dx with du over 2x. The x's goes away. We can push the 1/2 out in front. Push that u to the 1/2 as u to the negative 1/2. And now we go through power rule. Okay, go through power rule. We get u to the 1/2 over 1/2. Flip that 1/2 to be 2, cancel that with that 1/2, a plus c shows up. Now I'm going to go ahead and try to solve for c. So 4 goes in for x, 5 goes in for y. We solve for c, we get c equals 0, and then we can update our general equation, and so that's going to match answer choice B. Right, number 5, which differential equation has the slope field shown? So a couple of things I noticed as I'm looking here. We have a place where there's a slope 0 when y equals 0, and there's also a place, we don't see it, but it looks like it's a slope 0 when y equals negative 2. So based off of those two items, what will allow a slope to be 0 at 0 when y equals 0, and also allows y prime to be 0 when y equals negative 2. And we see that will be the case with A, right? A is the only one where it'll meet both conditions. Okay. And also you see that all across x, when x is negative 2 or when x is negative 3, or sorry, when x is 2 or when doesn't matter what the x values are from one end to the next. Looks like it's not even dependent on the x value. These are all the same slopes at each of these lines here. So that indicates to us that this slope field is based purely on y values because the x input has no impact on what the slope field's steepness are. All right, number 6, which function is a possible solution for the slope field shown? So what that means is, now if you look at the difference between 5 and 6, 5 are in terms of a differential equation. So these equations will give us kind of a idea as to where each of these points are graphed. Now, number 6 are not derivative. These are general equations. So for general equation, we're going to require a macro view of this. So we want to kind of look at the flow and the pattern of these slope fields. So if I start at one point and just kind of follow the flow of the graph, we see that the shape that comes out of it looks like e to the x. So plus 1, because of the fact that that plus 1 kind of takes the e to the x graph and shifts it up 1 unit. So if you're looking at y equals equation and trying to match with the slope field, then you're going to look at the overall flow and pattern. But if you're staring at the derivative form, then you're looking at each individual slope segment behaviors.